The purpose of this video lesson is to give you a brief introduction to significant figures and their relationship to measurement. For this lesson, you will need your notes packet, your yellow objective packet, a pencil or pen, and a highlighter. The learning goal to be accomplished here is learning goal 1C, to determine the number of significant digits in a measurement. Significant figures are all the digits in a measurement that are known for certain, plus one estimated digit. Or, as you can understand after doing the Are You Certain lab, all the digits that are recorded in a measurement. The origin of significant figures is that all measurements that we take in science have some natural limitations. The precision of the instrument that we use to take the measurements puts a limit on the number of decimal places our measurement can have, and that limitation is going to be reflected in the number of significant figures in a measurement. While it's very easy to know how many significant figures you have in a measurement when you're the one who's taken the measurement, it's a little bit more difficult to determine exactly what numbers are known for certain when you're looking at a measurement that somebody else has taken. In order to figure out the number of significant figures in a measurement that somebody else has recorded, we have 5 relatively simple rules. Rule 1. All non-zero digits are significant. We assume that if the digits are not zero, that somebody did either measure or estimate those digits. Captive zeros are significant. They're often called sandwiched zeros because they're trapped in between two numbers that are non-zeros. Leading zeros, however, are not significant. They're just there as placeholders to keep the decimal place shoved over to the left. Trailing zeros can go either way. Sometimes they're significant, sometimes they're not. So Rule 4 tells us that trailing zeros will be significant only when a decimal point is present. The decimal point doesn't have to be near the trailing zeros, it merely has to be present someplace in the digit. We're going to learn to use a decimal point very judiciously to help tell people exactly how far our measurement went. And our last rule is that counting numbers and defined conversion factors have unlimited significant figures. This is because when we count things as individual items, or when things are defined relative to one another, there's no uncertainty in that situation, and therefore we have an unlimited number of significant digits in the measurement or the conversion factor. Let's look now at some examples of each of these rules. Rule 1 is a very simple rule. It says that all non-zero digits in a measurement are significant. So the measurement 24.7 centimeters has 3 significant figures. We know exactly the 2 and the 4, and the 7 is an estimated digit. The significant figures in a measurement are all the numbers that are known for certain, plus one estimated digit. The measurement 16 meters has 2 significant figures. The 1 is known for certain, and the 6 is an estimate. And the measurement 35.87 centimeters has 4 significant digits, with the 3, the 5, and the 8 being known for certain, and the 7 being our estimated digit. Rule number 2 says that captive zeros are significant. Notice that each of these numbers has some zeros that are captive or sandwiched in between digits that are non-zero. So in the measurement 7,003 liters, we have 4 significant digits. In 102 millimeters, we have 3 significant figures. And in 10.35 milliliters, we have 4 significant figures. Rule number 3 is that leading zeros are not significant. Essentially what this means is that when we are counting significant figures, we're not going to start counting significant figures until, as we move from the left, we have encountered our first non-zero digit. So as we move from the left, we have a 0, a 0, a 0. The 7 is our first non-zero digit, so in this particular number, I have 2 significant figures, the 7 and the 1. In the measurement 0.42 feet, I don't count that leading zero, so this number has 2 significant figures as well. Sometimes you have different types of zeros in a number. This number has two leading zeros, which are not significant, but then it has a captive or a sandwich zero, which is significant. This number has three significant figures, those three significant figures being the 9, the 0, and the 2. Sometimes it's a little easier to figure out which digits are significant and which digits are insignificant if we look at the number in scientific notation. If I take the number 0.0902 liters and put it into scientific notation, I get 9.02 times 10 to the negative second liters, and it becomes very easy to see where the three significant digits come from. The two leading zeros disappear as we go into scientific notation, leaving us with the 9, the 0, and the 2 as being our significant figures. Rule number 4 says that trailing zeros, those would be zeros on the right-hand side of the number, are significant only if a decimal is present. Since the number 43.00 miles has a decimal point present, the two zeros at the end of the number are significant, and this number has four significant figures. The measurement 43.00 tells us that the person who took the measurement knew the 4, knew the 3, knew that there were 0.1 of a mile, and to their best estimate, believed that there were 0.100 of a mile as well. The measurement 700 yards, however, without a decimal place, only has one significant figure. The person who took this measurement, the way they have it recorded, is indicating that the 7 is an estimate and they don't know anything else. If we have a measurement like 700 millimeters or milliliters that we really believe is 700 milliliters, we can add a decimal point at the end of the number, causing those two zeros to become significant. The measurement 700 milliliters is saying that we know it's a 700, and we know that it's 0.10s, and to our best estimate, it's also 0.1s. That's a very different measurement than our 700 yards, where the 7 was an estimate. And here's a mixture of leading zeros and trailing zeros. The two leading zeros do not count as significant. However, the two trailing zeros do count as significant in this number due to the presence of the decimal point. This is another one where putting the number into scientific notation helps clear up any uncertainty about which digits are significant and which digits are not. Once we put it into scientific notation, the two leading zeros disappear and the trailing zeros will remain. When moving a number from standard notation into scientific notation, it is important that you keep the zeros that had been significant in the first number. Make sure that you don't drop those when you convert into scientific notation. Rule 5 deals with things that we count and things that we define. If I have a room full of students and somebody asks me how many I have, I would count you one by one, and there would be no uncertainty. When I say that I have 27 students in my classroom, there's no chance that I have 26.5 or 27.4. 27 students is an exactly counted number. Another set of numbers that have infinitely many significant figures are conversion factors. Things like 60 minutes equals 1 hour. 60 minutes is the very definition of 1 hour, and there's no uncertainty in these numbers either. Both the 60 and the 1 hour, and thus this entire conversion factor, are considered to be perfect conversion factors and therefore have infinite significant figures. Do not, however, fall into the trap of believing that all whole numbers have infinitely many significant figures. There are often times when we estimate about how many of something we have, and we didn't actually count in every individual item. For example, if we go to a football game on Friday night and we look around the stadium, we might say, there's about 2,500 spectators here. What we're saying when we say that is that we know there are at least 2,000, but not 3,000 people in the stadium, and to our best estimate, there's about 500 more than that. This number, because we didn't count the actual spectators at the event, only has 2 significant figures, and it has some uncertainty built into it. The other thing that we need to lay down as a standard in this class is how we're going to round. The rules for rounding in chemistry class are really no different than the rules for rounding in math class. You're always going to look at the number one position to the right of the last number you want to keep. If the number you're looking at is less than 5, keep the last digit the same. If the number you're looking at is 5 or greater, increase the last digit by 1. For example, if I wish to round the number 87.043 meters to 3 significant figures, the first thing I'm going to do is figure out which 3 digits I'm going to keep. I'm going to keep the 8, the 7, and something in this position right here. The number I'm going to look at to decide how to round is then that 4 right there. Since 4 is less than 5, I'm going to keep the 8, the 7, and the 0. I'm going to leave the 0 the same instead of rounding up. If I want to round the number 0.01552 meters to 2 significant figures, I start over here on the left. Leading zeros aren't significant, so I don't start counting until I get to my first non-zero digit. So here's the first digit I want to keep. Here's the second that I want to keep. I'm now going to look at the digit one space to the right of the last digit that I want to keep. That number is a 5. The rule says if it's 5 or greater, I'm going to round up. So rounded to 2 significant figures, I now have 0.016 meters. Hopefully this lesson has taught you how to count the number of significant digits in a measurement. Next time we meet in class, we're going to learn how to take our rules for counting significant figures and our rules for rounding and figure out when we add or subtract or multiply or divide numbers that we've measured, how many digits we get to keep on our answer.